Hello everyone, now we're going to solve Cambridge IGCSE Physics October-November 2024 paper 4-3. Number 1, A1. State the difference between a scalar quantity and a vector quantity. So a scalar quantity only has magnitude, no direction, but a vector quantity has both magnitude and direction. Number 2, define momentum. So in physics, right, if you see them asking definitions, you can also write formulas for that. So momentum is just mass into velocity. B, a test car crashes into a barrier to test the safety features. The test car has a total mass of 950 kilograms. It is moving with constant velocity from time 0 for 4 seconds, and at 4 seconds the car hits the barrier. So, hits the barrier. 1. During the test crash, the resultant force acting on the car is 27,000 newtons. The car takes 1.5 seconds to come to rest, and the deceleration is uniform. Calculate the initial velocity of the car. So just look at the given information and think about what we can calculate. And the previous questions, they also hint about momentum and stuff, so we can actually calculate for change in momentum using these two values, right? Because change in momentum is equal to force into time, and you can say that is 27,000 into 1.5, which is 40,500 kilogram meters per second. So we know that the final momentum is going to be 0 because it stopped. So if we want initial velocity, you can actually calculate from here. So we can say that this is the initial momentum that we have. So you can write something like velocity equals to momentum divided by mass. So 4050 divided by, we have 950 kilograms as mass, and that will be equal to 42.63. so on. You can take that and round that to two significant figures and get 43 meters per second. 2. On figure 1.2, sketch a speed-time graph to show the motion of the car from time 0 until the car becomes stationary. So in here, what does it say about the initial motion? Say is moving with constant velocity, and this is a speed-time graph. So it will have a horizontal line. This should be a straight line, right? Until 4 seconds, and then it got hit, so then it will decelerate with uniform motion. So deceleration is uniform. Therefore, the gradient of the line, it will be constant. It will be a straight line, and then speed will decrease. So it will look something like this. 2a. Describe an experiment to determine the spring constant of a spring. State the apparatus that you need, details of how to take measurements, and how to calculate the spring constant. You may use a space below to draw a labeled diagram as part of your answer. So we have to think about setting up an experiment. So when you think about spring constant of a spring, what do we need, right? So you need to refer to the equation. So equation is that force, if you apply the force, this is the spring constant that we'll be looking for, and then this is the extension. So this is a formula that is associated with this experiment. So you have to look for these two variables to calculate this thing. So first we attach the spring from somewhere, so the drawing would is not okay, but it should be clear. So this is a spring, right? And then you attach something like a mass, and this mass it says label diagram, right? So you can just say this is like the spring, and then this is a mass, like a load. Let's just say this is like 5 newtons, right? And this is after attaching, and you have to look for attaching, which means it will the spring will be extended, right? This is the extension. So let's just say this is like the original spring before being attached, and you get this original length, and this is like the final length. So you will find the extension between them, and that's one step. And this is the force, you already know it. And so you got these two like variables, so we can start writing. So firstly you have to like attach, okay, so at first you have to like actually measure the original length, right? So measure the original length of the spring using a ruler. Then attach a 5 newtons load to the spring and measure the final length. And you have to like subtract, so yeah, subtract the original length from the final length to get extension, maybe like to calculate extension. And you can use this equation, right? So use the equation F is equal to kx to calculate for spring constant k. And now we've got this apparatus we mentioned about spring, and we can actually include the ruler as well, and details of how to make measurements, right? Maybe we can even include about like looking the scale perpendicularly to avoid parallax errors and stuff. And maybe that's more like paper 6, but you can include, I guess. And for something like more to add for experiments, it's to repeat, right? To reduce errors and random errors and stuff. So let's just repeat the experiment is 3 times and take average to get more reliable result. Okay. The figure 2.1 shows a baby in a baby bouncer. The baby bouncer consists of a holder suspended from a spring. The baby pushes his feet on the ground and bounces gently up and down. Okay. 1, 2 springs Q and R are tested to determine their spring constants. Each spring is tested up to its limit of proportionality. So define limit of proportionality. It just means what it sounds like, right? Limit of proportionality. If you reach beyond that point, right, the spring, its extension, will no longer obey Hooke's law, which means it will be no longer proportional to the force applied. So you can just write the point beyond which the extension of a spring is no longer proportional to the force applied. Table 2.1 shows the results of the test. The total weight of the baby in the holder is 120 newtons. Calculate the extension of each spring for this weight. So you can just divide, right? 120 divided by, for Q, 120 divided by 7.8. That is 15.38. You can just take 15 cm. And then 120 divided by 1.1. 109, that would be like 3, so 110 centimeters. Okay, 3. The unstretched length of each spring is 25 centimeters. State and explain which spring would be more suitable for the baby bouncer in the figure 2.1. So I can look at the spring, right, and look at the extension. 15 and 110, like 110 is like too big. It is definitely too big. So you may not want to use R. Q would be more suitable. Because, and if you look at the total length from here, from the, let's just say this is like the scene or something like that, and then it's only 140 centimeters, and if the extension is like 110, then cannot cannot fit in there if it extends that much. So for Q, we can just say R, the extension of from spring R is too large. Yeah. So 3, figure 3.1 shows a portable shower used on a campsite. The bag is filled with water. The water is heated using infrared radiation from the sun. A1, explain why the shower bag is painted black. So black is a good absorber of radiation. So black color is a good absorber of radiation. To explain disadvantage of radiation from the sun being the only source to heat the water. So this is asking about the reliability of the sun, right? It isn't available 24/7. So we can write it isn't available 24/7, as it cannot work if there is no sun, or maybe at night, during nighttime, this kind of thing. So B, solar energy is a renewable energy source. State 2 other renewable energy resources. There are loads, you can choose any of them. Any of the ones that you know. So I would say the obvious one is the hydroelectric and wind energy. C, during the day, the sun shines on the shower bag, and some of the energy in the infrared radiation from the sun transfers to the thermal energy stores of the water. The water absorbs 60% of the energy incident on the bag. The temperature of the water rises from 10 degrees Celsius to 43 degrees Celsius. The mass of the water in the bag is 40 kilograms, and the specific heat capacity of water is 4,200 joules per kilograms Celsius. Calculate the energy incident on the shower bag during the day. Show your working. So just think about where we can start, right? It is asking for the total energy, and let's just calculate how much energy it gets, right? So specific heat capacity, C is equal to delta E divided by m delta T. So this is 4,200, and we don't know the energy. So this energy is what the water absorbs, right? this is not the final energy yet, because like not all of the energy incident is absorbed by the water, right? Here it says only 60%, so we still need another step. Energy divided by mass is 40 into 43 subtracted by 10. So for energy we get 4,200 into 40 into 33, and that's something like 5544 is equal to 5544 3 zeros joules. And yeah, this is only the 60% yet, so we have to calculate for the 100%, right? This is sort of working with efficiency. So efficiency, you can write the equation also. Efficiency is equal to useful energy output divided by total energy input into 100, because it's given with percentage. So 60 is equal to this is what we're looking for, right? Useful, this is what we just calculated. I'm so sorry, this is only 2 fourths to 3 divided by energy that we're looking for. So that will be 55544 3 zeros divided by 0.6. That is, we get 924 and 4 zeros. So we can just write the standard form to make it a bit neater, right? And to take two significant figures, 9.2 into 10 power 6 joules. For a figure 4.1 shows a ray of light as it enters the side of a plastic block. The ray of light passes from air into the plastic. 1. State how the speed, wavelength, and frequency of the wave in the plastic block compare with their values in the air. So this is the light ray. So the light ray in a medium that is denser, the speed decreases. So we can write speed is less, right? Yeah, speed is less. And wavelength is so we have this wave equation, right? V is equal to f lambda. So and frequency is constant. This has to be constant because it is like the identity of a wave is considered by that frequency. So if it changes, then it will be a different wave. Can be like that. So something has to be constant in one equation. So as velocity decreases, wavelength also decreases. Is shorter, and frequency is constant. You can say unchanged. To show that the refractive index of plastic is 1.4, show your working. So n is equal to sine I by sine r, right? So sine I is 45 degrees, sine r is 30 degrees. So if you use a calculator, you get root 2, right? Root 2 is 1.414 or something like that, and that is rounded to 1.4. So calculate the critical angle for the plastic. So critical angle n is equal to 1 by sine IC. So n is actually n is 1.4, 1 by sine IC, and you can, so inverse of sine 1 by 1.4, that is 45, some 45.58, something like that, and take two significant figures, you get 46 degrees. B. Figure 4.2 shows the same plastic as in A used to make optical fiber. A ray of light is passing along the fiber. One carefully continue the ray of light until it reaches the other end of the fiber. So this is like total intended reflection, right? It uses this concept. So I have to make sure like this maybe touches here. It should be a straight line, though I can't draw straight lines here. So and then here, then probably escapes like this. So one thing you have to make sure is that the I and R, they're the same. Like for because of the laws of reflection, right? Yeah, like that. So to state two uses for optical fibers. So this is like used in a lot of places. One thing that that's kind of obvious is about endoscopes, right? In medical situations, we use endoscope, and also like for cable TV, you use this fiber to transmit information. So you write there. So there are other many instances as well. You can choose and write about what you know. 5. Figure 5.1 shows the metal sphere S. The sphere has been charged with a negative charge, A1. There is an electric field around sphere S. On figure 5.1, draw 4 field lines to show the pattern of the field and indicate the direction of the field with arrows on the lines. So let's just draw the lines first, and you notice that those charges, they are spread evenly across the sphere, so we have to have a uniform electric field. And for the direction, right, because the direction of electric field shows how it's affected the positive charge, so it will be attracted inwards. So figure 5.2 shows the position X next to sphere S. A small negatively charged particle is placed at position X. State the direction of the force on the negatively charged particle X due to the electric field around sphere X. So we have to think about the force on the negatively charged particle, and because they are like negative light charges, it will repel from each other, so it will experience like a force to the left, outward, right? Because it's getting repelled. So we can just say like force is to the left, repels. 3. The negatively charged particle at X is released from rest. Describe the motion of a small negatively charged particle due to the electric field around it. So in the previous question, right, we just said force is to the left, so its motion will be like away from the sphere, right, to the left. And one thing you have to think about is that it's experiencing a force, so there will be resultant force. There is a certain force, there will be acceleration. So we can write about that. It accelerates due to the electric force and moves away from the sphere. We can just write like accelerates away from the sphere in short form. B. Figure 5.3 shows sphere as being sprayed painted. Sphere S is negatively charged. As the paint particles exit the white nozzle of the paint sprayer, they become charged with a positive charge. One explain why the paint particles spread out when they leave the nozzle. So they all are like light charges, right? So they will definitely repel from each other. So since they are light charges, they repel each other. Okay, 2. The sphere can be painted by hand using a paintbrush, suggesting explain one advantage to using charged paint from a spray gun to the to sphere S. So it's like more it sticks better, right? Because they are unlike charges, they attract each other. So you can say that the paint particles stick better to the to the sphere. So like can be like more adhesive, you can say, and that is because unlike charges attract. So you can say that positive paint particles are attracted to the negative charges on the sphere. And 6A. A car windscreen is covered in condensation, small droplets of water. Thermal energy is used to remove the droplets of water. The thermal energy is provided by 3 resistors on the windscreen. Figure 6.1 shows 2 possible circuits for the 3 resistors. The 3 resistors, they are identical. So circuit A, you can see that this is connected in series circuit, and circuit B is in parallel circuit. So describe 2 advantages of using circuit B. So if you use parallel connection, right, you actually get equal amount of voltage. So they will get the full voltage from the 12-volt car battery. And if one fails, right, the other 2, they will still be working. So we can write those 2. So firstly, each resistor receives full voltage from the car battery, and if one of the resistor fails, the circuit will still work. You can just write the other 2 will still work. To describe in terms of the water particles, the process by which the water droplets are removed from the car windscreen using the heater. So this is the process of evaporation. So because those water molecules, they gain enough energy, right, they can escape from the surface. You can write like that. So water evaporates since molecules receive enough energy from the heater to escape from the surface of the water. So you can say that not all of the water molecules, right? So this happens to the most energetic water molecules. B. Figure 6.2 shows a circuit containing two resistors, P and Q. The circuit is powered by a 12-volt battery. 1. Calculate the current in resistor Q. So you have this equation of V is equal to I in R. Current, it will 12 volt will be divided by 70. So 12 by 70 is equal to 0.1714. You can round that to two significant figures, ampere. And you should also write this substitution, right? I is equal to 12 divided by 70. To calculate the energy transferred electrically, 1. The current calculated in B1 is present in resistor for 5 minutes. So energy E is equal to power, right? Power into time. And power is IV T. So you have 0.17. Voltage is, because it's a parallel connection, you get the full voltage, which is 12. And then time is 5 minutes. So I have to convert that to seconds, because that's SI unit, right? So if you calculate that, 0.17 into 12 into 5 into 60, you get 612 joules. So you can round that to 610 joules. 3. Energy is transferred from the battery by electric current. State the energy stored in the battery. So we know that it is chemical energy from the battery, right? And 4. Calculate the total resistance of the circuit. So this is a parallel connection, so you have to use that formula, right? So 1 by R that you want is equal to 1 by R1 into 1 by R2. And so 90 and 7, you can just substitute. So actually you can, if you put that in calculator, right, you just need to put it like this in shortcut. So 6300 into 160, 39.375, and you can take two significant figures, 39 ohms. 7. Figure 7.1 shows a barrier at the entrance to a car park. The wooden barrier arm has a weight of 60 newtons, which acts through the center of gravity at the position shown on figure 7.1. A. Initially, the wooden barrier arm is horizontal. Using figure 7.1, calculate the clockwise moment of the weight of the wooden arm about the pivot. So this is the weight, this is the distance. You can just multiply them. It just gives 1 mark, but yeah, let's just write an equation. Probably so distance. It's not worth it to write just for 1 mark. If you have extra time, you can, but it's probably not worth it. Force into perpendicular distance from pivot. We're not sure, sometimes the marking scheme gives 1 mark for 2 points, right? You can do it like that sometimes. 16 to 1.7. That is 102. So just 100 newtons meter. He even gives the unit for you. 2. The wooden barrier arm is in equilibrium. Right? No net force, no net moment. The mass on the soft iron bar A is 23 kilograms. Calculate the distance between the pivot and the joint holding the soft iron bar A. So now this is like 3 marks, so you have to write all the things. Equilibrium, which means total clockwise moment, is equal to total anti-clockwise moment. So what is a clockwise moment in this case? From this point, right, you already calculate that 100 is equal to total anti-clockwise moment is E into 23 into 9.8, right? Because it is the mass. I have to work out for the force multiplied by 9.8. So D will be equal to 100 divided by 23 into 9.8. Divided by you get 0.44365 and so on. You can take two significant figures. That is in meters, right? Yeah. B. Figure 7.2 shows a coil attached to a power supply placed below the soft iron bar A. Okay. One statement explains what happens to the wooden bar arm when the switch in the coil is closed. So this becomes a full circuit, and this will start becoming a magnet, right? Electromagnetism, and this soft iron will be attracted to it. So it will kind of like it will no longer be in equilibrium, right? It will be attracted, so it will rotate, and you have to explain why as well. So the statement is that the arm rotates in anti-clockwise direction. So why, right? As the circuit becomes complete, the coil will become magnetized, and produces magnetic field around it, which will attract the soft iron bar A. Or you can write something like coil become an electromagnet. That is more complete, right? Electromagnet. Is it 2? The switch is opened. The operator decreases the potential difference across the coil, and switch is closed. State and explain how the effect on the wooden barrier arm compares with the effect in B1. So there is less potential difference, which means less current, and that will like make the arm a bit like move slowly, and not as much as the one in the first question. So you can say the arm will move more slowly. And why is that? Because the current will be reduced, and there will be smaller current, which means the magnetic field, the strength of the magnetic field will decrease. So if there is current, there will be magnetic field. Yeah. And 3, a student suggests that the soft iron bar A is replaced by steel bar. Explain why steel bar is less effective than a soft iron bar in the barrier. So soft iron bar is a soft magnetic material, and steel is a hard magnetic material, which means that it takes more time for steel to be magnetized or to be attracted by the electromagnet at the first place. So it won't be like real time working thing. So and it's also gets magnetized permanently, which means that if you disconnect, even if you disconnect the circuit, it will still be connected to the electromagnet. It's not even an electromagnet at the point anymore. It will be a permanent one. So I would say that it's harder to magnetize steel bar so slower to attract the iron bar and becomes permanent magnet. So this bar A, the iron bar, this red bar A would be attracted to the coil even when the circuit is open. 8. An isotope of boron is used in the treatment of cancer in the brain. Boron sticks to cancer cells in the brain. A. The isotope of boron is bombarded with neutrons, then undergoes fission to form lithium and alpha particles. Describe one difference between fission and fusion. So one difference, right? So I have to think of the most important one, which is like fission splits nuclei, whereas fusion joins nuclei. So I have to think about more than one nucleus that will be in plural form. 2. A nucleus of boron B contains 5 protons and 5 neutrons. Complete the nuclear equation for this fission reaction. So it says 5 protons, you can write 5 down here. 5 neutrons, so 10. And then this thing, this side of equation, this side has to be equal. But for lithium, we don't have periodic table or anything like that. We don't remember anything. So that we have to know about the alpha particle. Just 2 protons and 2 neutrons. And this side is 11. So the side has to be 11 as well, 7 and 3. B. The alpha particles destroy the cancer cells. I suggest and explain one reason why alpha particles are more suitable than gamma radiation for use in this treatment of brain cancer. So, this gamma radiation, right, is more very, very powerful, and it will penetrate through a lot of things that we don't really want. So alpha particle is just enough, right? So we can write that alpha particles are less penetrating. So it's safer for the patient. So they will not damage other cells or body parts. C. Other cancers are treated with gamma radiation. Alright. Describe one safety precaution a nurse or radiologist takes during this treatment. So safety precaution, right? For the gamma radiation to be stopped, you need to use protection stuff, and that will be using a shielding, a lead apron, probably a lead shield, because it can absorb the gamma radiation. So wear let's say use a lead shield to absorb gamma radiation. You can also write something like reduce exposure time and increasing the distance and stuff. But I think like in practical, right, you have to do something can really control about those time factors and stuff, probably. Logically works, right? Now a figure 9.1 shows a diagram of a transverse wave. From figure 9.1, identify all the lengths which represent one wavelength. Okay, all the lengths. So wavelength is like the distance between two adjacent crests or troughs. So yeah, first thing we see Q. Probably somewhere from here to here. There's nothing describing that. Oh, here V. R is not a wavelength. Yeah, I think that's also just Q and V. B. Hydrogen in a very distant galaxy emits electromagnetic radiation which is observed on the Earth. Scientists on the Earth measure the wavelength of the radiation from the very distant galaxy. The wavelength is 918 nanometers. On the Earth, hydrogen in the laboratory emits electromagnetic radiation wavelength 656 nanometers. Although nanometers is like 10⁻⁹, which is very, very small. Name the effect that the scientists observe and state what this shows about the very distant galaxy. So what the scientists are observing is like the increase in wavelength, right? So it's just what we observe, not the actual one. The actual one has to be the same, right? So why does the observed wavelength increases? Well, it's because of redshift. It's called redshift. As the galaxy, the very distant galaxy, is moving away from the Earth. See, table 9.1 shows a wavelength of electromagnetic radiation from hydrogen observed in the laboratory and from 3 galaxies. The galaxies are different at different distances from the Earth. Describe what table 9.1 shows about the motions of the galaxies and state what this suggests is happening to the universe. So, a gas tube, so this is the reference point we have to look at. A nearby galaxy, like not that different, distant, very different, very distant galaxy, very, very different. So, you can say that those galaxies, they are moving away from us, but at different rates. So which means that if those galaxies are farther away, then they are moving away much faster. So the farther the galaxies are, the faster they are receding from the Earth, which means that the universe is expanding. So 10a. Stars are more massive than the sun. Stars more massive than the sun can eventually form black holes. Describe how a black hole can be formed from a more massive star. So, firstly, right, now the sun that we're seeing is a star in like main sequence stage, and it keeps on burning, right? Hydrogen fusion, but eventually that hydrogen will run out, and when that happens, like other like big elements, they will do the fusion, and then it will expand into red supergiant, right? For stars that are more massive than the sun, so they will expand into red supergiant, and eventually it will explode as a supernova. So When that happens, there will be a core remaining inside, and if the core is still bigger than like 3 solar masses, then it will become a black hole. Or if it's small, then it will become a neutron star, something like that. But now we are taking the root of a black hole. So firstly, we can write about hydrogen begins to run out, and the star fuses helium and other larger elements. The star expands and forms a red supergiant because it's more massive than the sun, and then it explodes as a supernova, which leaves behind very dense core in the middle, which collapses to form a black hole. So B, the star system V404 Cygni contains a black hole. The system is approximately 7,800 light years from the Earth. Describe what is meant by light year. So light year is a distance, right? Distance that even light takes 1 Earth year to travel. So we can write the distance traveled by light in 1 Earth year. To calculate the approximate distance from V404 Cygni to the Earth in kilometers, so that's 7,800 light years, and light travels in or you can if you remember 1 light year in distance meters, and you can just plug that in, which is 9.5 into 10 power 15, or maybe because it asks for kilometers, right? 12 kilometers. This is the distance of 1 light year. Or if you do not remember, then you have to take the longer way. This is the distance. This is the speed of light, and because it's 1 Earth year, right? We have to calculate for 365 days. 365 into 24 hours into seconds. So this whole value will be equal to 9.5 into 10 power 12. 10 power 15 meters, because this is a meter. We have to convert that to kilometers again. And that will be equal to 7.41 10 power 16. 412 10 power 16. You can take that as 2 significant figures. Already have kilometers here. So yeah, this is the end of the paper, and good luck with your studies.